Hey, welcome back. In this lecture, we are going to be talking about the graph class interface and implementation that we use for our own graph class. But it's not just to talk about code here, but more to sort of talk about some of the conceptual ideas involved in that design, and to deal then with the difficulty of the implementation and why it would be implemented the way it is. So the TAs will be going over maybe a little bit of the actual code. Our goal here is to talk about more of the conceptual ideas behind that code. The graph class, as we're going to be dealing with it, is a little bit different than some of the other structures we've seen, or a little bit different than some of the other interfaces we've presented you with so far, I should say. Not that it has to be, or not that the other interfaces had to be different, but up to this point, we've mainly just dealt with structures, most often as dictionary structures. We talked chiefly about inserting and removing when explaining an access, when explaining what the difference between the array and list implementations of the list ADT would be. We talked about insert and remove and find on a binary search tree, on an AVL tree, on a B tree, on a hash table. A lot of the structures we talked about, we mainly concern ourselves with looking up and inserting and removing. And that could be something we would do with the graph class. But if we're going to deal with just inserting and removing edges and inserting and removing vertices and looking up edges and looking up vertices, that doesn't really help us too much. The kinds of things we would need to use a graph for are things where we'd want to say, well, we have a particular vertices are our cities, and let's look at all the departing edges so we know what roads go from this city to other cities, and then from there, look at what departing edges go from that city, because we want to find out how to get from city A to city X or something like that, where there's a lot of traversal we'd be doing over the vertices and the edges themselves. So our goal is really to be aware of the graph structure through an interface, to say that I have here a vertex of some kind, and that points to some edges, those through edges point to other vertices, which have edge connections to other vertices, and so on. And it's most helpful to us if we have some awareness of that setup, as opposed to if all we have access to is some sort of black box, and I say, or green box in this case, because I'm using a green marker. If we have I'm just inserting and removing stuff from that black box, that's fine for an implementation of a dictionary ADT, but for the kind of things we want to do with this graph class, that's not going to be fine. And the same thing would have been the case back when we talked about trees. We did say that for a general tree implementation, we might use that to implement, say, a corporate hierarchy, where I say, okay, I have, I don't know how many children I'm going to have in advance, but I've got some, subtrees here of some root node, and this is the CEO of the company, and then these are the managers with their departments, and for this manager, those are the sub-managers, and those are their employees. And so in that case, that would be an example of something where knowing the tree structure was important. If we just simply said, hey, I've got a big collection of stuff that I'll dump employees into and pull employees out of, then that wouldn't tell us anything about the tree structure. And so if I wanted to, then I could have, on this kind of a conceptual view, an interface could have provided me with that ability to say, take the fourth subtree and return it. And so I can then return a copy of this subtree, and then I have that manager's department that I can then parse over and pay employees or whatever. And similarly, though we wouldn't find it quite as useful, when I had a binary search tree, I had 15 and 10 and 12 here, and 21 and 28 and 18. And I could have just as well said, okay, give me the right subtree of that binary search tree, and then I'd return a copy of that, and that would be a binary search tree as well. Now, the binary search tree strength was mainly that we could look up quickly, so it was more used as sort of a dictionary, an implementation of the dictionary ADT. I want to be able to insert and remove and find quickly, and so that's why I set things up that way. We didn't really have as much need for pulling off individual small subtrees. The binary search tree tended to be, the structure was designed to optimize lookup. It wasn't a structural representation of a real-life model. It was just a collection of stuff that we are ordering in a helpful way, where some sort of a corporate hierarchy or something like that, in that case, the structural setup of the tree would be something that was really important to us. It wouldn't just be a matter of, oh, we just got a collection of nodes. I don't really care what order they are as long as I can search fast. That was sort of how we looked at the binary tree. Okay, the issue wasn't oh, we really want 21 to be the right child of 15. The issue was, if 21 is the right child of 15, and the way these things are set up, that helps us look up things faster than if we had a one long linear linked list. And so there's two different ways of viewing things. And one, the structure is important from a conceptual point of view, from the client point of view. And the other, in this case, we're really more concerned with saying, usually from the client point of view, we don't care about the structure. This is just implementing a dictionary ADT, and I just want to dump stuff in and pull stuff out. And the structure is there to make the implementation work quickly, but the structure isn't something the client needs access to. Or in this top example, that would be something where the reasons we've set the tree up as far as structure goes, the way we have, is a fundamental part of how we're going to use it. The client of that code needs access to that structure through the implementation. It needs to be able to say, for all my children of the root, give me each of the subtrees that those children are roots of. Give me this subtree, give me this one, give me this one, give me this one. So I can return the departments one by one. If we hide this all behind a black box and say insert and remove employees and that's it, it's really not useful to us anymore. So there's that fundamental idea where the way the data structure is arranged could be just arranged that way for the helpfulness of lookup and find and so on. Or it could be arranged that way because the actual structural arrangement is important to the client as well. And a graph would be an example of a structure where, more often than not, the actual structural arrangement is going to be very important. We don't, generally just saying, hey, dump in vertices and dump in edges, it's not going to be too big of a deal. We're going to actually want to know the arrangement of those vertices and edges and be able to move across them as a client, much like the corporate hierarchy type tree in this example. Now, the reason that we mention this is that in both cases, we probably want to hide an actual tree node. We don't want the user to be able to mess around with the left and right pointers of the node containing 15, and likewise the user shouldn't be able to mess around with the pointers of the root in this case either. However, that doesn't mean that the user shouldn't have the knowledge of the existence of those nodes. Rather, the user or the client of this code should simply sort of view this conceptually as, I have 4 children of the root, and give me child 1, and give me child 2. And the actual implementation should be hidden so that you would then return, okay, return whatever pointer 1 points to, return whatever pointer 2 points to, but you wouldn't give the client visibility to that pointer, and so they couldn't actually set it to something else. They could simply go through the interface and say, give me client 1, or subtree 1, give me subtree 2, and so on. And likewise for our graph, we don't need to give the client access to our actual vertex and edge nodes that, however we're implementing things behind the scenes. All that's important is that they have a conceptual abstract view of this is a vertex and a conceptual abstract view of this is an edge. And that's what's going to be important. The client can say, I'm referring to a vertex, I'm referring to an edge, but they don't need to have access to the implementation of that vertex any more than the client in this tree example needs access to the implementation of the tree. The client only needs access to, conceptually, hey, give me subtree 1, give me subtree 2. Not give me, I want to set the pointer that points to subtree 1. And so that's an important distinction, that you can draw this and say you have subtree 1 and you have subtree 2, and that's a conceptual model. This is the implementation model, where we actually say you have some subtree with pointers of its own, and here you have some subtree with pointers of its own. And so there's a difference between giving the client, returning a copy of that subtree, and returning a pointer that can be manipulated. And if it seems like I'm beating a dead horse, sorry. But this is really important to understand the distinction between the two, because that's going to factor into how we design the interface of the graph class. The interface of this graph class is going to be one in which we allow an abstract picture of the vertices and edges through the idea of iterators, basically. We've dealt with this before where we had a list. We said, I don't really know how this is implemented, but I have an abstract picture of things element by element through the idea of iterators. And likewise here, we'll have the same idea. I can have some graph, let's say it looks like this, where I have here A and B and C, and maybe C is connected to E, and E is connected to G, and then we've got here, this is connected to D, and there's an F, and maybe that's all there is. Maybe A is connected to F too. So we'd have there 7 vertices, and the idea here then becomes, what is important is to have some sort of access, some sort of ability to say, this is the vertex I'm referring to. So I can say I have some sort of vertex v1, and v1 would now be some variable that could point to A for us, not in a get at the implementation of A way, but in the same way the iterator did, where we're more or less just sort of marking A, and we can have some other vertex v2 that's sort of marking G in a way. We're saying we're marking this, and we can move this marker from G to D to E to B and say I'm referring to different vertices at different times. And likewise with the edges, I can say I've got an edge, E1, and now I can have some E1 where I'm sort of marking this edge with my iterator. And I can have another edge, E2, which is in effect marking this edge. Not accessing the implementation, but simply saying, here's the edge you want. And so, though the way we approach this will be a little bit different than you've seen so far, fundamentally this is how we'll approach access to our graph, is we'll have markers to edges and markers on vertices. And I'll be able to say, given this vertex, and which vertex am I talking about? Well, the one that V1 marks. I have no idea how to access it or even how it's implemented or anything else. I just know I've got some variable V1, and V1, somewhere in its internals, is pointing to some vertex. And given that vertex, print out its label or return the list of its departing edges or whatever else we want. And same thing with the edge. Given this edge, which edge? Well, the edge referred to by E2. I've got some variable E2. I have no idea how it's implemented or what it points to. I just know it's conceptually referring to some edge. Given E2, return the endpoints of E2. Print out the labels of the endpoints of E2, something like that. So we won't be able to actually dereference this pointer. The E2 will be all we have, the name E2, and we'll be able to use E2 as a marker to a vertex. So the question is, what kind of instance methods do we have, member functions do we have on this iterator? We had before plus and minus and the dereference, the star, and so on. And do we have the same things with these iterators? And the answer is no. And the reason is the iteration we want to do here is a little bit more complex than we had before. When we had a linked list, we're just going from first to second to third to fourth to fifth node, and that was it. So there was just really one way to traverse, or we could traverse backwards. But there was one order to traverse in. Likewise, with the AVL tree, we could say, well, we want to traverse an in-order order, from which, of course, was lexicographical order since it was a search tree and thus ordered by the less than or greater than symbol. And so, as a result, we knew we had the ability to go, if we did an in-order traversal, we were going from smallest to largest element. And so, likewise, we could just say that's our one order. And as you do plus or minus, you're going forwards or backwards in that order. Where here, there may be a number of things we want to traverse over, especially with edges. Say I have an edge. Well, as I move from edge to edge to edge to edge, am I trying to traverse over the list of all edges? Or am I trying to traverse over the list of departing edges of some source vertex? Or am I trying to traverse over the entering edges of some target vertex? So especially if this was a directed graph, we might say, well, a given edge is leaving some vertex and it's entering some other vertex. So in other words, one vertex is its source and another vertex is its target. And then certainly the edge is on the list of all edges as well. And so that's something to concern ourselves with. The idea that, well, when I say plus in an edge, do I want the next edge in the list of all edges, the next edge in the list of, if this was a departing edge, or if these were directed edges, now E2 is leaving A and entering F. Do I want the next edge that is leaving A, which might be the A to C edge? Do I want the next edge that's entering F, which would be the C to F edge? Or do I just want the next edge in the graph in general? So it's not immediately clear what plus would mean. And the answer then the way we can get around this is we can say, let's not build plus or minus directly into our iterator classes themselves. Let's instead say if you want to change one of your markers, your edge marker or your vertex marker, you pass it into the graph class itself. You send it into some graph member function, and the graph member function will send back the new value of the iterator, or alter the iterator, or however you want to code things. But the idea here would be, instead of trying to build plus plus and dereference and all those things, there's already an ambiguity here, where if we define all the plus plus to mean move to the next edge in the list of all edges, then we'll have to say, well, you pass the edge into a special graph function to get back the next departing edge, or you pass the edge into a special graph function to get back the next entering edge of the target vertex. And so if we're going to have to do that for some of the possible traversal ways, let's just do it for all of them. Let's not confuse the issue by saying, well, plus plus does one thing, but all the other kinds of traversals, you need to send it into the graph class special. Let's just send everything in the graph class all the time, as opposed to picking one special case out and saying, oh, well, this kind of traversal, that gets to be plus plus. And all the other kind of traversals you need to send into a graph function. Instead of mixing them up, let's just say all the kind of iterator access will go through the graph class, because some of it has to. And so, I mean, that's one possible design decision, and that's the design decision taken here. Instead of building plus plus and dereference and all those sort of things into the vertex and edge iterators, instead we'll simply use the vertex and edge iterators as markers. We'll be able to assign one marker to point to another, so I can say, V1 equals V2, and that will say, well, now the V1 marker points to the same spot that V2 does. I'll be able to say that create a new vertex marker to be a copy of an old one. We can create a new vertex marker, say just vertex V3, and not assign it to anything. And that now points to null until we assign it. I can compare two markers and ask if they're the same, pointing to the same place or not. So we'll allow ourselves to do assignments and comparisons, but nothing else. All sort of access of the actual data will go through the graph class, and all the markers we'll be able to do is say, we'll assign one marker to another, or see if one marker points to the same place as another. They will literally only mark the vertices, only point to them and say, that's the vertex I'm on. But if you want to do anything with that vertex or with the edge marker, you pass the vertex or edge marker into the graph, into an appropriate graph class function. And we did that a little bit when we talked about, say, the list class, and we said, well, you could pass in a list iterator into the remove function, or it was called erase in our code. And then that would erase from the list the node the iterator pointed to. And so you couldn't erase from the iterator class. You had to send the iterator into the list class to erase what the iterator pointed to. And we're just extending that idea. Or same thing with insert. If you wanted to insert a value, you said, well, pass the iterator into the list class, also pass the value into the list class, and then the result will be to insert that value after that iterator. And now we're just taking that and saying everything we do is going to do that way. If you want to print out the value, the key, the label of a vertex, send the vertex into the graph class, and that will if you send the vertex into the graph class, that will lost my train of thought here. Sorry. That will then print out the label. Or you say, I want to delete a vertex, send the vertex marker into the graph class, and that'll delete the vertex at that marker. So that's how we're going to approach things. And so that means then we can do things like this, where I can have, say, methods or functions such as, say, here's our vertex return type, and we'll have add vertex like that. And so the way we use this code would be to say vertex v1 equals g is our graph variable, g dot add vertex. And what that would do is, given an existing graph, we would, for example, just go ahead and say create a new vertex h, and then point v1 to that. So we declare v1, and then we say when we add h, we then return a marker to the new vertex, and then v1 can point to the same place as that new marker. Similar to when we said l.begin for our list. We had a list L, we'd say L.begin, that sent back an iterator, and then we had our own iterator, it1 equals L.begin, and we're saying our iterator it1 is assigned to be the same iterator that was returned by our begin method. Except begin didn't create a new node, and this does. But that's the same idea. This sends back an iterator or a marker that v1 points to the same place as that marker points to, just like we might have said it1 equals L.begin. Same kind of idea. Likewise, we can have a method here, delete vertex. I may have called this insert vertex in the code, but this is the fundamental idea here. So there we simply say, if I just say g dot delete vertex v1, that's like the erase function in the list class. Send in the marker to a vertex, and the graph class will get rid of that vertex. And so that says, well, since v1 is pointing to h, I get rid of h. And that's that. Now, of course, we could have done the same thing for an edge. I could have had edge, add edge. But just saying, hey, add edge doesn't really make much sense because you get an edge floating off in the middle of nowhere. If I just say, hey, create me a new edge and return a reference or a marker to it, I say, hey, great, I create a new edge, and then, now E1 is going to point to that new edge. And of course, that doesn't make any sense because you can't have an edge floating out in the middle of nowhere. You need to have an actual endpoint on each end of the edge. And so what that means is to define an edge, we really need to pass in the two vertices it should be between. An edge just doesn't just float off in the middle of nowhere. It's between two specific vertices. So if I have V1 indeed pointing to A and V2 pointing to G, then let me do that. Let me do this a different way. Let's say that this is V1 here. If V1 points to C and V2 points to G, what my add edge method will do is say vertex takes in a source vertex, CE. Sorry about that, S-O-U-R-C-E, not S-E. Sometimes I have a brain flip. And vertex target. So I have the source and the target. And so the way I would use that method would be to say edge E1 equals G dot, I declare E1. Of course, it was created already. Let me make this E4, just so I'm not using an edge we used already. So edge E4 equals G dot add edge, and I'd pass in V1 and V2. And that would be the kind of syntax I'd use there. Send in two vertex markers, and what I want to do is add an edge between them inside my graph, and then return a marker to that edge so that E4 can point to that same edge, can be a second marker to that same edge. And so what that would accomplish then would be, we'd say, well, now I'll have some edge E4, and what that will point to is a new edge between what V1 pointed to and what V2 pointed to. And so that would be that. And of course, we could do a delete edge the same way we did delete vertex. That's the basic idea behind adding vertices or adding edges or removing them. Basically, you'll have, whenever you add a vertex or add an edge, you'll send back a marker or an iterator that then can be stored in some variable. The question, of course, is what if we didn't do that? What if we added a bunch of things, but we never bothered using the return variables, or we used them and then erased them or whatever? And the point is, at some point, we've got the graph sitting there like we had before. Here was the original graph we talked about. C, F, maybe we had this edge as well. And then, we had here E and G and B points to D and blah, 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 blah. There we go. That was the original graph I put up before. And so the question is now, that being our graph, if we're given that graph, instead of having a bunch of markers to all the variables already, how can we make use of this? It's the same thing as with the list. As we inserted nodes in the list, we didn't always have an iterator pointing to every node. We could extract an initial iterator, begin, and then say, well, I create some iterator, start at whatever begin points to, and then move the iterator down the list one by one. And we want to do that as well. We want to say, okay, give me some marker to the first vertex, and then move me to the next vertex, and then move me to the next vertex, and then move me to the next vertex. And that's exactly what we did with iterators before. We said our iterator equals L.begin, and then we said iterator plus plus, iterator plus plus, iterator plus plus. And we started the iterator at the very first node, and then moved to the next node with plus plus, and to the next one with plus plus, and with the next one with plus plus, until we were equal to whatever the end iterator pointed to. That's sort of null position spot. And we'll do a similar thing here. what we're going to be dealing with is to say, what I'd like is to just return some vertex. I need to have a method or function to return the first vertex, just like we had a function to return the first node in the list. The issue, though, is that the first node in the list was very clear. It was the head node. The first node in the AVL tree was very clear. It's the minimum node. What's the first node in the graph? And the answer is, it doesn't matter. Yeah, if we have string labels on the vertices, we could arrange them in alphabetical order, but we don't have to. It doesn't matter. Back in the lecture we did last time, remember, the graph is a set of vertices and a set of edges. And a set is not ordered. It's simply a collection, but we don't have any first element, second element in the set. It's just a collection of elements, and we're concerned with, is an element in the set, is the element not in the set, but we don't have a first and a second and a third element necessarily. What this means is that if I want to traverse across the list of vertices, except in specific applications where I might want to build some sorting ability into the graph for that purpose if I find it useful. But in general, I don't need to have the vertices back in any order. All I want is that if I say give me the first vertex and then give me the next one and then give me the next one, if I look at 7 vertices in that manner, I expect they'll be the 7 vertices in my graph. I don't expect to traverse C, B, C, E, C, B, G, C, D, C, A, B, C, E, B, F. I don't expect to keep coming back to C and B over and over and over again as I traverse. I expect that if I look at 7 vertices, the way the implementation is set up, it will give me a different vertex each time. Give me the first, give me the next, 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 give me the next. Okay, now I'm done. And I expect to be able to do that. To be able to say, give me the first vertex and then give me the next vertex over and over again until I have no more vertices to look at. I expect if I do that, that'll take me through each vertex exactly once. 7 vertices, and then I'll be done with the traversal. Not that I'll keep coming back to C each time and saying the vertices get spit out in the order C, F, C, E, C, B, C, C, A, C, C, G, C, D, C. You know, that's going to be a pain. So outside of that, we can have the vertices back in any order. If the function, if the class wants to return them in the order A, B, C, D, E, F, G, great. If it wants to send them back in the order G, F, E, D, C, B, A, great. B, E, D, G, C, F, A, fine. C, E, D, G, B, F, A, fine. The order doesn't matter. All that matters is that we get the sequence of 7 in some order. So from the implementation standpoint, probably the easiest thing to do is to send them back in whatever order the implementation stores them in. So let's say the implementation had a list of vertices, for example. I'm going to write it up here. If we had, say, E was the first vertex, and then A, and then G, and then C, and then B, and then F, and then D, our implementation could say, well, if I ask for the first vertex, I'll get E back. And then what I can do is say, well, if I want the next vertex after that, I should get A. And if I ask for the next vertex after that, I should get G. And if I ask for the next vertex after that, I should get C, and so on. So what we can do is write 2 methods. We can say vertex, first vertex, and vertex, that's the return type, next vertex, vertex V. And those would be 2 functions we can use. When we call first vertex, that's exactly like calling begin. We said add vertex was kind of like calling begin, except add vertex was actually creating a vertex and sending back an iterator or a marker to it, or begin just sent back the iterator or marker to the first vertex that already existed. First vertex here will be the exact equivalent of begin. Take your first vertex in the graph and send back an iterator to it, or a marker, or whatever you want to call this vertex class. But this is some sort of an iterator to your vertices. Send back an iterator to your vertex, your first vertex. So it's the exact equivalent of begin. And next vertex is basically the idea of taking the plus plus operator and building it into a graph class function. What we're doing here is we're saying, send in your iterator, and I'll return the one after that. So instead of calling plus plus on your vertex V, you instead send V in, and it sends back the vertex after that. So the kind of code you'd write here for this, we'll be coming back to this slide in a moment, would be something like vertex v1, which here is an analogy to when we said our, list int iterator it1. And then we can say v1 equals g dot first vertex, which is the exact analogy to it1 equals l dot begin. And then I'll need some while loop here. That will be my analogy to while it1 is not equal to l dot end. And then within here, I would say, and I'm not going to worry about printing, I'm just going to do traversing, I'd say it1 plus plus. And inside this while loop here, I will say v1 equals g dot next vertex v1. Shouldn't have drawn that line down the paper, now it's interfering with things. So that's the idea here. We have here the vertex v1, set v1 to our first vertex, and then while, and we'll have to build a condition code in here, and then say v1 equals the next vertex, and let me draw this line out a little larger, because it's not going to show up well on the scanned-in slide. That's what this line is down here. So instead of saying plus plus, since we're going to do everything through the graph class, that's how we'd have to handle this. We say send in your vertex, and I'll return the vertex after that. So what would happen here is the first vertex returns an iterator to E, and so therefore V1 points to E. And then when I say send in V1 to next vertex will say, well, I'll access the pointer hidden inside V1, and that points to E. I'll grab the next built into E's node. Each of these would have been some node. And the next points to A, so what I'll return is some marker to A, and then we're setting V1 to hold that marker. So now V1 points to A. And then when I pass in V1 to next vertex again, we're saying, okay, now I can access the internal pointer of V1. That points to A. Grab its next, that's G. I'll send back a marker to G, and V1 stores that location. And so now V1 points to G. And then I say, well, I pass in V1 to next vertex again, and the implementation says grab the hidden pointer of V1, that points to G, read the next field, that's C, send back a marker to C, and then V1 is set to hold that, and now V1 points to C. And we'll basically do that over and over again, and that'll be the point of this list. Or I'm sorry, this loop. We'll be running this line over and over again and saying, well, V1 points to the first vertex. When you send in a marker to the first vertex, you get the second vertex back. When you send in a marker to the second vertex, you get the third vertex back. When you send in a marker to the third vertex, you get the fourth vertex back, and so on and so forth. And so that's how that works. Now, what we need to complete this loop is the equivalent of our end here. We need the equivalent of saying, well, if V1 is pointing here to the very last node, D, I then note that the next element is in my list would be null, and so when I send V1 now into next vertex, what I should send back is a pointer to null, and say, well, now if I send here this in, then what I get back is a pointer to null, and then V1 set to that, so that V1 points to null. And we can do that just by having a method isNill. We pass in some vertex V, and this returns 1 if the vertex points to null, and it returns 0 if it doesn't. And so then if we do that, we can then say, while it's not true that our V1 is nil, continue. So we say, give me the first vertex. And if it's not true that that's nil, then you'll set it to the next vertex. And if it's still not nil, then you set it to the next vertex. And if it's still not nil, you set it to the next vertex. And if it's still not nil, you set it to the next vertex. And is it nil now? Oh, yes, it is. So this condition is not true, and so you leave. And that would be how you'd go down the list one by one. you'd say, first vertex, is that nil? No, so move it to the next vertex. Is that nil? No, so move it to the next vertex. Is that nil? No. Is that nil? No. Is that nil? No. Is that nil? No. Is that nil? Yes. And so that would be how that would work. As soon as you've called next vertex on a pointer to D and gotten a pointer to null back, then in that point up in the while loop, the condition will be read. This time V1 will be null, so is nil is true, not is nil is false, and you'll leave the while loop. And that's pretty much the exact equivalent of asking that, keep going as long as the iterator is not equal to n. So it's slightly different syntax. Now instead of building these operators into the iterators, which we could have done to some extent, the decision's been made just to put have everything run through the graph class. But in spirit, it's the same idea. You have an iterator, you assign the iterator to some first vertex, you can compare it to see if it's the end of a list of vertices or of edges. There's the analogy here for edges. And then you can set it to the next vertex as well. And so you have in spirit the parallel to the iterator stuff we've done so far, but the syntax, the way of dealing with it, is slightly different. So don't get too thrown by it, because it's not too different in spirit from what we've already done. And of course, then you can have the same concept in reverse. So I can have a last vertex and previous vertex pair of functions that will allow me to start with the last node and traverse up to the front, similar to my minus minus or my reverse iterators did. And I can have the idea of having same functions on edges to let me go across the list of all edges in one direction or the other. Or for adjacent edges, I can say in one direction or the other, give me the list of all adjacent edges of A. Or if this were a directed graph, in one order or the other, give me the list of all the edges that depart A. Or in one order or the other, give me the list of all edges that enter E. So you might have different functions available if it's a directed or undirected graph, but that would be how things could work. And so that's kind of the interface. You'll see more of it in section, and you'll be able to mess with it as you look at the graph class, which you'll be using on the last MP8. But that's the essential idea behind how we're approaching this. It's basically an iterator-based concept. It's just now there's a slight variation in that the iterators are being used through the graph class instead of building functions into them ourselves. This is just one sort of quick credit line. This appears in the comments of the class as well. This is, if I remember correctly, some German research institution that designs a bunch of basically data structures, and then you can if you sign certain agreements, whatever, you can look at their source code, blah blah blah. But they freely publish their interface to their classes on the web, and so we went out and searched. Our graph class that we were using was really really bad, and so a few years back we went out and searched the web and just kind of poking around, seeing how other people wrote graph classes, and kind of absorbing some ideas and saying what might be a good way to deal with graph classes and such. What have other people tried? Let's consider other ideas before pounding our head on the desk trying to reinvent the wheel ourselves. And we came across this organization, this research group, whose web page is listed in the code to the graph class comments. And we liked their interface, so we borrowed it. And it was freely published on the web. We coded the implementation ourselves, and I'm about to talk about that. But pretty much I want to give credit because they were the ones that inspired our interface. And so take a look at they have a huge data structure library. Go ahead and take a look at the web page listed in the comments of the graph class if you're interested. But we implemented some of that interface that they had, and then coded figured out a good implementation, coded it all up ourselves. And so with heaps of fun. This implementation is really nasty, as you'll see in a moment, but it makes the interface run very nicely, and that's why the implementation will be so nasty, but most clients won't really have to deal with the implementation too much, but it makes the interface very elegant and very fast. And so, but anyway, as far as inspiring the interface, I wanted to give credit where credit is due, and so there you go. You don't need to remember that, by the way. That won't be on the test. But that's sort of the academic integrity issue. I want to kind of give credit as appropriate. So that said, the question then becomes, how can we implement this? And one way to approach this, you're going to want to write this down on a piece of paper somewhere, because I won't be able to keep coming back to this graph. There's going to be huge amounts of writing on the next page, and we won't be able to fit this on. So let's consider this graph. A graph where we have 3 vertices and three edges, an A to C, an A to B edge, and a C to B edge, which is a very, very simple graph. And it's going to require a pretty complex implementation just for that, as we shall see. The way we're going to approach this is that we're going to, in trying to implement this structure, we'll say, well, firstly, let's have a list of vertices. This is going to be basically a form of the adjacency list structure that we talked about in the last lecture. Except to start with, instead of an array of our vertices, which is what I had shown you, we could have had a list of vertices, and then still off of each vertex a list of the relevant edges. But we're first going to say, instead of an array of vertices, let's have a list of vertices. And so we can have here a vertices that look like this, where I have here A, B, and C. So those are our three vertices. And the question is, well, I said they were a list, so we definitely want to connect these. What we will also do is make it a doubly linked list, because that will allow us to go from first to next to next to next, or from last to previous to previous to previous very easily. So we'll make them doubly linked. And in order to facilitate easy removal, we'll also make it a circularly linked list. That is, the last vertex will point to the first, and the first vertex will point to the last one. And so the reason for that is then, no matter where you are in the list, removal of a node in a doubly linked, circularly linked list is simply a matter of saying, let me go back to here just once. If I have a node anywhere now, I can simply say, this is my arrangement. And if this is what I want to remove, it's very easy to say previous, or if this is C, it's cur previous next equals here, and point this to there, and say cur next previous equals cur previous, and point this to here. And now if you notice, in just 2 pointer assignments, the current node has been completely removed from the loop. I don't have to worry about special cases. Well, if this is the last node, don't do that. Only remove one or whatever. There's no special null cases to deal with. Now every single node in the list has a previous and a next, and it's very easy to remove from a doubly linked list. That's circular linked. Every single node follows the exact same procedure. Make 2 pointer assignments and then delete your pointer to that node. So for that reason, we've made it circular as well. The idea here is now any node in this list I'll be able to remove very easily. And so the question is then, well, how do we know we've reached the end? Well, if our next equals, we need some pointer to the front of this list. So if our next equals v pointer, we know that we're at the end. And so as we traverse from first to next, when our next equals what v pointer points to, or if our next vertex is our first vertex, then we should send back a null iterator instead. And that's sort of our signal that we've reached the end of the list. If the client's asking for the next vertex, and our next vertex that we see is actually the first one, then we should really send back a null. So that said, we can do the same thing with the edges. I had an edge from A to C. I'm just going to write AC, meaning the edge from A to C. I had an edge from A to B, and I had an edge from C to B. And we can do the same thing here, where I'll have a doubly and circularly linked list of edges. Well, so the question now is, what I'm missing is the ability to say, from the vertices, I have edges. This is all fine and good in that, of course, I need some pointer to the edge list as well. If my only concern here is to be able to traverse across the list of vertices and traverse across the list of edges, this is excellent. We would presumably store some data here as well. So I'd have some collection of data for my vertices and some collection of data for my edges, if there's a key or something, or if I have some information record or whatever. And there's a number of different ways of doing that, but I'm just concerned about the connections right now. So I can traverse through the list of all vertices in both directions, and I can traverse through the list of edges in both directions. What we don't have yet is any connection between the vertices and the edges. And so one thing we might do, and the file picture I want to look nice, so I'm going to remove this for a second and just quickly sketch out the exact same thing. So here I have A, and here I have B and C, and here's the AC edge, and here's the AB edge, and here's the CB edge. Now, one thing I might do is say, well, I could build a list of pointers to the relevant edges. So I could say, well, A is supposed to point to AC and AB. And so I could say, I could, of course, store all the information here, but it'd be nice just to store it once. I have the edge here, and what this can do is it can say, well, that node will point to the AB edge, and that will point to the AC edge. And then here, well, B doesn't depart from anything, and C only departs from the, here, the CB edge. Or that edge departs C. So we could do things that way. And that's sort of our adjacency, basic adjacency list makeup, where we say the A list holds pointers to the two edges that depart A, the C list holds pointers to the edge that departs C, and the B list doesn't hold anything. But since we've got these edge nodes created already, we may as well go ahead and have entering edges as well, because we may want to have a list of entering edges. So I could say here, well, the A list doesn't enter anything, or I'm sorry, nothing enters A. There's two edges that depart from A, but nothing enters A. Nothing departs from B, but there are two edges that enter B, namely this edge and this one. And there's one edge that departs from C, and one edge that enters C. So we could set things up like that now, where in a sense, every one of these edges is pointed to by two of these nodes. Instead of having duplicate copies of these edges, instead of saying, well, we'll copy the information here, and we'll have it here as well, we allow the edges here to be arranged in a list of all edges. And then here we can say, well, the source points to the edge, and the target of that edge also points to that. The source, which here is C, points to that edge. The target, which is B, also points to that edge. Here, the source, which is A, points to the edge. The target, which is C, also points to that edge. And so we can do things that way, and that gives us now quickly the ability to traverse down the edge list and to grab the individual edges. Now, from the individual edges, we might want to get to the source and the targets, so we might well have here a pointer to A, all the way over here, and a pointer to C, which, would go all the way over here. And likewise, here we might have a pointer to A and a pointer to B, and here we'd have a pointer to C and a pointer to B. And that way, every vertex could have a pointer to its source vertex and its target vertex. And this would point to A and to B, and this would point to C and to B. So from every edge, we can get to its source and target. So we might add those pointers as well. You can see this is going to start to look really complex. In addition, we might want to point to its representative spot inside this list. I might say, the AC edge, it would be nice if I can get from here back to, this is the AC node in the AC list. And it might be nice now here's the, likewise, it might be nice if I can get from here down to these two nodes. Because if I can, then I can say, well, given this edge, if I want to get rid of this edge, I could easily access that node and say, well, maybe if I make this list doubly and circularly linked, I can easily remove this from that list. And if I have access to this node, then if this was doubly and circularly linked, which would just mean it points to itself, then I can easily remove that node from that list. Given a pointer to that node, wherever it is, I can pull it out of that list easily. Which raises the question, if I'm going to point from here to here and from here to here, if I need to say A's departing edges list needs to point to the AC edge, and the AC edge needs to point to its corresponding node in the A's departing edges list, then why make them different nodes? It's helpful to draw that way, but really we can make them the exact same node. That is, what I could have inside an individual edge would be something as follows. I've already drawn this part. I have the previous edge and the next edge. And then, this is just, I'm just putting that in for notation on this piece of paper. This is the AC edge, for example. what I could have here is 3 pointers, a pointer to the source and a pointer to the next source edge and previous source edge. And what I could have here is a pointer to the target vertex and the next target edge and the previous target edge. The question is, what the heck do I mean by that? Well, we've already talked about the pointer to the source and the pointer to the target. This edge can contain pointers to the vertex that is its source vertex and pointer to the target vertex. So we can point to our endpoints and retrieve the endpoints of an edge in constant time. In addition, what I can say is, well, if I have this is my vertex A, and here's my departing edges list. What this list will be is, I need a pointer to the next edge in my source. This is, these are all the vertices for which A is a source. Well, I need a pointer to the next edge for which, these are all the edges for which A is a source. I need a pointer to the next edge for which A is a source, and the previous edge for which A is a source. And likewise, each of these. This needs a pointer to the next edge for which A is a source, and the previous edge for which A isn't a source. Let's build those pointers directly into the node. And similarly for the departing list, when we have an entering edges list, when we're saying all the edges, such as we looked at before for B, these are all the edges that enter B. Well, instead of having different nodes here that they're doubly and circularly linked, and each of them points to the corresponding node, the node correspondingly points back to there, let's simply say, well, I need those next edge that has B as a target and previous edge that has B as a target pointers. Let's build them right into the node. Or in other words, what we will do here is say the following. I will say, well, here A's entering edge list is null, B's departing edge list is null. So we'll actually store a list of the entering and the departing edges for each vertex. That means we don't want to stuck with the departing edges like we were in the diagram I drew last time for the adjacency list. I can actually look at all the edges that depart A and all the edges that enter A. What I'll do here is I'll say these two edges both have A as a source. So what I'll do here is I'll say these are my target pointers, because I'll need 2 more here. These will be my source pointers. And I'll say this points to the next vertex in my source and the list of vertices, list of edges that have A as a source. This points to the previous vertex, previous edge in the list of edges that have A as a source. And then, of course, these are doubly and circularly linked. That is, what I've done here is link in a list all the edges. I have only 2 of them, but I could have far more. All the edges that have A as a source. Both of them, of course, point back to A with their source pointers. And A's departing edge list points to the front of that. So when I want to traverse over all the edges that depart from A, I point from A's departing cell to here. And then I can traverse to here, and I could just go around in circles forever between those 2 nodes. Likewise, each of those 2 nodes can point back to A, or you can, starting at any one of these nodes, go to the others. So starting at any vertex that's got A as a source, I can reach the source A. I can reach all the, keep saying it, starting at any edge that has A as a source, I can go to the source vertex A. I can traverse, I'm in the list already, so I can keep traversing in the list of all the other edges that have A as a source. And of course, from A itself, I can reach we pick some random edges, the first one, and I can reach the first of all the edges in my departing edges list. Similarly, I can do the same here for B. I can say, okay, these are the target these pointers here are the target pointers, so I say this is the next edge for which B is a target. This is the previous edge for which B is a target. And then I'm just going to draw this. That should be circularly linked as well. So now I have a list. It's only 2 nodes long, but it could be more. I have a doubly and circularly linked list of all the nodes that consider B a target. Both of their target pointers point back to B. So from any edge that has B as a target, I can reach B in constant time. Similarly, for any edge that has B as a target, I'm already in the doubly linked list of all nodes that have B as all edges that have B as a target, and I can keep traversing around that list. In this case, it's only 2 nodes, but it could be far more nodes if I wanted, if I had a larger graph. And I can traverse over and over again through the list of all nodes that all edges that have B as a target. And likewise, B's departing edge or entering edges list can just, okay, some random node out of that list of edges point to that, and that's your start of your edge list. So I can go from B to say, here's my entering edges, and I can just traverse around that list. And then finally here, when a doubly and circularly linked list has only 1 node, then it just points to itself, because the next node is itself and the previous node is itself. And so here we have the target pointer is C, and that node is in C's entering edges list. And here, again, this is the only node in C's departing edges list. Its source is C, and here's the start and only node in C's entering edges list. And as you can see, that's a huge, huge garbled mess, even on this slide with just 3 nodes and 3 vertices. As your graph gets larger, there's no way on earth you'd want to be drawing this on paper. But if you code the implementation carefully, it'll take care of all these connections for you. But that's basically, as far as pointer connections, what we're dealing with. Given any vertex or edge, I can remove it in constant time. I can insert after or before it in constant time. Given any vertex, I can reach the first node of the departing or entering edges list in constant time. I can reach the next or previous vertex in constant time. Given any edge, I can reach the next or previous vertex in constant time. I can reach the source and the target endpoints in constant time. I can reach the next or previous vertex in whatever list of departing edges this edge is in. You can reach the next or previous vertex in that list in constant time. And whatever list of entering edges this edge is in, you can reach the first or next edge in that list in constant time. So there's a lot of things here that can be done in constant time. Basically, you have a pointer to all the information you need. So instead of having to traverse all over the graph for it, you have a pointer directly to it. Every edge points to its source and target, and it's also a part of a doubly linked list of the departing edges of whatever its source is and the entering edges of whatever its target is. And of course, then you have a list of all edges as well. And so that's the implementation that can very efficiently, or one implementation that can very efficiently implement the interface. It's basically a form of adjacency list, because from each vertex we have a list of the vertices that depart from it, instead of having a list of all the vertices and having to figure out at each node, is this one part of this or is it not? So that was the adjacency matrix, where we would have had a list to every vertex, and we'd say, well, we have a 1 or a 0 stored in every node. Here we have only a list of the vertices that we actually point to from departing edges, and also from entering edges as well. So this is an adjacency list format, but unlike the graph last time, we've got a list of vertices instead of an array of vertices, and we've got both departing and entering edge lists rather than just departing edge lists, and then there's a lot of extra information stored in those edges as well, rather than just the letter of the relevant vertex. So this is a far more complicated version of an adjacency list, but it's still an adjacency list, and it will be how we actually take care of our graph implementation. So I will leave it at that. You'll get plenty of chance to look at this some more, but that at least is your introduction to a possible very nice interface and implementation for a graph class, and how you can take a very complicated variation on a very simple idea that we looked at last time, and therefore make a very useful structure out of it. What we will talk about next time is the issue of finding shortest paths in a graph, and that will be an issue for next time. So I will see you then. Take care.